In this video, we're going to see how we can use the finite difference to approximate the partial derivatives. Basically, what we did in dimension 1 can be generalized to dimension 2 or to higher dimensions. And here is a way to approximate this partial derivative. Say, for instance, you want to approximate df over dx in xy. Well, as you would think, you can go either forward, backward, or central, and you will have not many problems to show that we have these equalities with the Landau notation O of h, O of h, O of h squared, meaning, by the way, that it is a second order approximation. Same thing for the derivative with respect to y. But as you can see, of course, we're going to do it with the variable y, as you would expect. So basically what I'm saying is that if you have a grid, then if you want to approximate the partial derivative df over dx or df over dy at xi, yj, it will be easy to do so by simply using these formulas. And we can look at the stencils that are here. And obviously, if you look at df over dx, then that will be horizontal. If you look at df over dy, then that will be vertical. All right. Now, what about second order partial derivatives? Well, what you can do is basically the same things that we did before. So here is the second derivative with respect to x, here is the second derivative with respect to y, and here is the second derivative with respect to x and y. And again, if you understood what we did in dimension 1, then basically this generalizes with no problem to dimension 2. I did that here using the central difference quotient, but you can adapt these formulas very easily to forward and backward difference quotients. Now, what you have if you have x equals xi and y equals yj? Well, simply where you have plus h or minus h, well, you just use the proper numbering system, and here is what you obtain. Of course, you can look at what is the stencil of these formulations. Well, here is the stencil for df, for d second f over dx squared. Here, and that's obviously horizontal. For the second derivative with respect to y, here it is. It's obviously vertical. And when it comes to the second derivative with respect to x and y, here is the stencil. Obviously, you need the points both to the left, to the right, above and below. Now, if we wanted to approximate the Laplace operator, then obviously what you have is you need to approximate the second derivative with respect to x and the second derivative with respect to y. So here is what you get. I just put the second derivative with respect to x and the second derivative with respect to y. What I have, therefore, is this, right? Which means that the stencil is what we call the 5-point stencil, which is basically the point that you're considering, ij, and the one to the left, the one to the right, the one above, and the one below. Now, what we're going to do is use this stencil and this approximation to actually approximate a PDE and solve the Poisson's equation minus Laplace u equals f on a domain omega.